Okay, so 3.2. F of x equals a to the x is an exponential function that passes the horizontal line test and therefore must have an inverse. The inverse function is called a logarithmic function with base a. The formal definition for a logarithm: for x greater than 0 and a greater than 0 and a does not equal 1, y equals log x base a. This is true if and only if x equals a to the y power. So we did this last year in Algebra 2, so we're just reviewing it. F of x equals log x base a is just function notation. And if you remember, y equals log x base a is true. The equivalent exponential form is x equals a to the y power. So in example 1, I want us to move up to a new level this year. It says use the definition of logarithmic function to evaluate each logarithm. So we really shouldn't be writing anything out, but mentally we'll think in letter A, the log of 32 base 2. You should be thinking 2 to what power gives me 32? What would that be? 5, right? 2 to the 5th, 2, 4, 8, 16, 32. All right, letter B, log 27 base 3 means 3 to what power is 27? 3, okay? Now in C, this might exert a little bit more brain power, the log of 2 base 4. Good job, it's really a square root. And to do the square root, that's the 1/2 power. All right, how about D? The log of 1 over 100 base 10. Negative 2. All right, Adam's on fire. All right, letter E. Log 1 base 3. 0. And the last one, log 2 base 2. 1, because 2 to the 1. Now I want to pause here a moment, because we will eventually get to problems with our calculator, and I want to make sure we're not using the calculator inappropriately. Do you remember it says that x has to be greater than 0? So if you see the log of negative 3 base 3, we should not even attempt this. But let's think about it in case that's not as clear to you as it is to me. The answer to a logarithm is the exponent in the exponential form. So if you think 3 to what power would spit out negative 3, you might think it's negative 1. But what's 3 to the negative 1? Oh, that's not negative 3. Can you think of a number that I could raise 3 to that would produce a negative 3? Imaginary something. Nice try, but there isn't an imaginary number that will do that. So be careful. This is called undefined. Do not put no solution or the no solutions symbol, because that tells me you don't understand. We don't have an equation here. Also, what if I had log 0 base 2? Okay, I'm going to make this one up. Log 0 base 2. 2 to what power would give me 0? Well, you might think, well, I'll just do 0. But what's 2 to the 0? There is no such number. And oftentimes we gloss over our definitions, where definitions are critical pieces of information. It says for x greater than 0, so you cannot put 0 or negatives inside a logarithm. Okay? All right, now we're going to look at an exploration here. If I have f of x equals 10 to the x and I want to fill in the table, well, I'm going to start on the right side because that's easier for me. 10 squared is 100. 10 to the first is 10. 10 to the 0 is 1. 10 to the negative 1 is 1/10. 10 to the negative 2 is 1 over 100. Do you remember that a log and an exponential are inverses of each other? So to do the next table, do you remember I can just switch the x and the y values because they're inverses. The logarithmic function with base 10 is called the common log, or the common logarithmic function. So on your graphing calculator, there are two buttons we can use on the keypad. So if I want to look at log 10, you're just going to press the log 10. And we probably didn't need our calculator for that, right? And then I have 2 log 2.5. And then for C, we really ought to not touch our calculator for that, right? Undefined. It is undefined. So common log, if you see log with no base, it is assumed base 10. All right, properties of logarithms. If I have in general the log of 1 to any base a, it's going to be 0 because a to the 0 power is 1. If we have the log of a base a, that's 1 because a to the first is a. So remember, the exponent on the exponential form is the answer to the log. If I have the log of a to the x base a, that's just x, because it's a to what power gives me a to the x, and it's the x. And then the fourth one is something we refer to as a one-to-one property. If the log of x base a equals the log of y base a, then their insides are equal. Then looking at example 3, excuse me, it says solve each equation for x. In letter A, if I have the log of x base 2 equals the log of 3 base 2, what's x?
3.
X is just 3. Now in letter B, do you notice I don't have 1 log equals 1 log, so I can't use the same strategy. So if I have the log of 4 base 4 equals x, how would I solve this? I don't want to know the answer right away. Tyler?
Second property up there is log a to the a equals.
Yeah, exactly. If you look at that second property, the log 4 base 4 is just 1. So x is 1. We will do more log equations in 3.3 and 3.4. Alright, in example 4, it says sketch the graph of f of x equals 2 to the x. And we're going to do 2 different grids here. And we know, as long as there's no transformation, we're going to use negative 2 to 2. I like to start with my positives and then follow the pattern. It's a little bit easier for me. 2 squared is 4, 2 to the first is 2, 2 to the 0 is 1. That's 1/2, 1/4. This is what we did yesterday with our exponential graphs. Don't forget to include your horizontal asymptote. So my domain is negative infinity to infinity. The range is 0 to infinity. I have a horizontal asymptote of y equals 0, and we have a y-intercept of 0, 1. Again, this is what we did in the previous lesson on exponential functions. Then in part B, I need to understand that a logarithm is the inverse of an exponential with the same base. So I'm going to make a table here, but I can just flip the table. And do you guys remember last year in Algebra 2 where we had those foldables and I came across another teacher who had done the table differently? I want to go ahead and refresh your memory because if you're doing these by hand without a calculator and you don't remember this, like what's another option? Well, here's the other option, and I really, really liked this coming across it last year, is if you look at log x base 2, I know that if I make x a 1, I know the answer to that. The log of 1 base 2 would be 0. And then I know log 2 base 2 is 1. Then the next nice number to work here would be 4. The log 4 base 2 is 2. Now what would be the next nice number to try? 8. Good job. Yeah. Because the log of 8 base 2 would be 3. So it doesn't matter to me which route you go to get your table. However, the only problem with this one is you have to understand that with a logarithm, it has a vertical asymptote, and you need to draw the graph in such a way that demonstrates your understanding. So let me explain that a little bit clearer. By actually drawing this. So I'm going to use the first table. If I have 4, 2, 2, 1, 1, 0, then here's 1/2 -1, 1/4 -2. Here's the general shape of a logarithmic function. So do you understand that it doesn't stop at 1, 0? It is continuing, and it's going to hug the vertical asymptote as it gets closer and closer to the y-axis as it's shooting down. So then let's talk domain. Domain is 0 to infinity. The range is -infinity to infinity. You have a vertical asymptote of x equals 0. And now I have an x-intercept of 1, 0. There is a little bit of a danger to using your calculator. It will sometimes not show this piece right here, and it'll just look like, because it's trying to connect dots from integer values, and so it may not be plotting the 1/2 and the 1/4. So you need to know, as your pre-calculus student, you're smarter than your calculator, and you have to make sure, because if you're asked to graph this, say on your quiz that you're working on, make sure you've got it coming all the way down here, even though your calculator might show that. Okay? So just be careful. Now let's pause a moment and let's compare the two graphs. Do you notice that the domain and the ranges have flipped? And they should, because they're inverses. I went from a horizontal asymptote to now having a vertical asymptote. I went from a y-intercept to having an x-intercept. And then do you remember last year, in my tool belt I had the light switch, and we talked about in the equation or on the graph you can switch x and y to create the inverse. But there was one other piece, and it wasn't in my tool belt though, is graphically, how else can you see an inverse of a graph besides switching x and y? Tyler?
Reflection over y equals x.
Good. If you consider, if we had put these on the same grid, my exponential graph would have reflected over the line y equals x to produce the logarithmic function with that same base. Okay? Alright, so any questions on graphing a logarithm? Okay, example 5 says sketch the graph of f of x equals log x base 10. So we don't have the exponential form, so let's just start with some convenient numbers. If I did the log of 1 base 10, I would know that f of x would be 0. I could pick 10. The log 10 base 10 is 1. And then what would be the next nice number? 100. And so the log of 100 base 10 would be 2. Okay, we can get a little lazy here and we'll just make it go 50 and 100. So you're going to have to guesstimate where 1 comma 0 is, 10, 1, and then there's 100 comma 2. Now here's what I was talking about. Here's the danger with using this table. It looks like it's almost like a square root function, but it's not. I know better than that. So I have to draw the extension shooting down to negative infinity. So I have domain is 0 to infinity. The range is negative infinity to infinity. I have a vertical asymptote of x equals 0. And we do have an x-intercept of 1 comma 0. The only time that domain and vertical asymptote and x-intercept are going to change is if you have shifted left or right. Okay. All right, any questions? All right, then let's do the natural logarithm, ln x. It says the function defined by f of x equals log x base e. We call that ln x, or the natural logarithmic function. Properties of natural logarithms. This will be similar to logs with base 10. We know ln 1 is also 0 because e to the 0 is 1. We know ln e is 1 because e to the first is e. Okay, this third one tends to be a little bit tricky. Ln e to the x is x, and think about it, e to what power is e to the x? Or when we get to 3.3 on Monday, we're going to refresh our memory on that power rule that says you can bring it down, and it's x ln e, but ln e is 1, so it's x times 1. The other one is e to the ln x, and it's like the e and the ln cancel and leave you with just the x. And then the fourth one, if you have ln x equals ln y, then their insides have to be equal. All right, try example 6 on your own. I'll give you a head start. It says use the properties of natural logarithms to simplify each expression. You should not be using a calculator. Then when we finish the notes, we're going to play a game of tic-tac-toe. The winning team will earn candy.
Oh, it is. I forgot I put it there.
Okay, letter A. I can rewrite 1 over e to the negative 1. So then ln e to the negative 1, the ln and e cancel, and you have negative 1. In b, there's really no work, it's just 5. E to the ln 5 is 5. Now, what do you know in c about ln 1? 0. 0 divided by 3 is 0. ln e is 1, so that's just 2. Okay? All right, now in example 7, use your calculator. Let's go 3 places. And you know where your ln button is. I really hope letter C did not push any buttons on your calculator. Okay, ln cannot have 0 or negatives inside it. So when you're done, check the board. I have all 5 of the answers up. Any questions on how you punch things in the calculator? You remember this from last year? Pretty easy. Okay, last example. Okay, let's refresh our memory here just from the beginning of the lesson. The inside of a logarithm must be positive. So it doesn't mean x has to be positive. It means the result of the inside has to be positive. So in letter A, if I want to find the domain, you set the inside greater than 0. So x is greater than 2, or in interval notation, that's parenthesis 2, comma, infinity. In letter B, you set the inside greater than 0. We subtract 2. And when you divide by a negative 1, that makes it x less than 2, which is negative infinity to positive 2. Let's pause here a moment, because that's weird, isn't it? This one's like 2 to the right, and the other one's negative infinity up to 2 on the left side. I want you to take out your calculators, and let's look at each one of those. If I have ln x minus 2, let's do zoom 6. And do you notice a few things here? It looks like the graph stops when in fact it doesn't. It just doesn't have any more points to connect it to. So there's my vertical asymptote at x equals 2. And then notice it is everything to the right of 2. Then let's go back to the y screen and let's make this ln 2 minus x and press graph. Wow, I mean that explains why it's on the other side now. Do you see that? So it still has the vertical asymptote at x equals 2, but it's the graph everywhere to the left of it. So that's pretty interesting. Now, letter C, this is a challenge domain. H of x equals ln x squared. There really actually isn't any work. This is more analyzing the situation. So we're going to play the game, what do I know? I know that the inside of a logarithm must be positive. Okay, we know that. What do you know about the inside of this particular logarithm? X squared.
Put a negative in there, it'll be positive.
Okay, great. If you put a negative inside and you square it, you get a positive. If you put a positive in and square it, it's positive. What's the only other situation to consider? 0. If you plug in 0, we have a problem, right? Because it says the inside of a log must be positive. It doesn't say it can be 0. So all the negative numbers I would try would work. All the positive numbers would work. And the only thing that doesn't work is 0. So my domain is the set of all real numbers x such that x is not equal to 0, or, for my interval notation fans, negative infinity to 0, union 0 to infinity. Now let's go look at that graph, okay? Let's see. Oh, this is exciting. So let's go ln x squared, and let's graph it. Ooh. Now, is this connected right here? No. This is a one vertical asymptote, and so it's coming the left side with a vertical asymptote and the right side with a vertical asymptote. Now I know some of you like to play around on your calculator with pictures. Now you have a new something to work with if you want, to make some kind of a picture. You can add that to your tool belt of knowledge. Now let's also, on example 8, let's talk about vertical asymptotes. In order to determine a vertical asymptote, you set the inside of the log equal to 0. You take the inside of the log, so let's go back through with each one. The vertical asymptote, if you set x minus 2 equals 0, the vertical asymptote is x equals 2. And what's interesting is if you set 2 minus x equals 0, and didn't we see that on the graph? And then in letter C, the vertical asymptote was x equal 0.